Hello and welcome to this lecture. So we saw a few problems on the z-test in the previous lecture. Most of those were like sort of standard textbook problems where the distribution is given and you had to work out the null hypothesis and alternate hypothesis and the distribution of the test statistic, the actual test depending on what is your testing, and then you write down this formula for the significance level, and that's the crucial thing, isn't it? Probability of rejecting null, given null is true, and given null is true, what is the distribution of the test statistic? That is something crucial for you to know. Once you know that, the calculation is straightforward, isn't it? The same calculation will come again and again and again. Okay, so in the next few examples, I'm going to do a couple of things. I will use some sort of real examples, real sounding examples, and pull the data from that. Number one. Number two, I want to bring in the role of the number of samples. Okay, so it turns out the number of samples is a crucial parameter in controlling everything. It's not wrong to say that most of your problems will go away if the number of samples increases. Okay, so this alpha and beta, right? Two types of errors. You want to keep the value down, isn't it? You want to reduce both alpha and beta. The only way to reduce them without trading off is to increase n. If you keep increasing the number of samples, both alpha and beta will keep on falling. Otherwise, you will end up in this trade-off. If you fix n, there's always a trade-off. Okay, so that's something important, very important in any test, not just z-test. But in this examples in z-test, I want to bring out this aspect of testing. Okay, so in general, this is true. Okay, if you have more samples, more good happens to you. But in practice, it might be very hard to get more samples. Getting more samples is expensive. You have to pay for more samples in most cases. Okay, so anyway, I mean, let's come back to those kind of practical aspects later. But let's get into problems where there are real situations, and you want to control alpha, beta, and you're trying to go towards number of samples. How many samples do I need? Sort of problems. These problems are very important. Okay, so let's begin with something very simple. Just to show you how, if you have very few samples, you're in very dangerous territory in making conclusions. Okay, so here is a question, sort of binomial distribution question. Depending on, I mean, the numbers are so small, you have to use binomial. You're trying to sort of, somebody reports that the vaccine hesitancy, people who don't want to take some vaccine is 20%. Okay, and you think it's maybe greater than 20. Okay, what you decide to do is to call some 10 people randomly, maybe representative of the distribution in the place. You call 10 people, and out of that, the 3 of them say that they are vaccine hesitant. They don't want to take a vaccine, or at least they're thinking about taking a vaccine. So that's the data you have. Only 10 people you've called. It's actually small. You'll see if you start doing these calculations, you'll get some bizarre answers, or at least some you'll be uncomfortable in some of the calculations. Okay. So what is the null hypothesis? Null hypothesis is, okay, so first always start with samples. I like to write the samples down. I think quite often you'll see this is implicit in the problem and people just don't write it down, and sometimes it can be a cause for confusion. So it's good to write down the samples. You have x1, x2 to xten, which you're supposing is Bernoulli, IID Bernoulli P. Okay. So notice this assumption IID Bernoulli P, it's fairly serious in your calculation, right? So if the 10 people you called were all living in the same house, this is probably not going to be satisfied. So you have to be careful about how you decide to sample and all that. All that is an important part of any study. Okay. What is xi? Xi is 1 if person is ith person is hesitant, and 0 else. Okay, so this is a sort of situation, and probably you're assuming this IID, and you want to find the probability that a random person is vaccine hesitant. Okay, so this is how it looks. So the alternative hypothesis, so the null hypothesis is that p is equal to 0.2. Maybe somebody did a very large survey and they found p is 0.2, and your alternative is that you think it's above 20. It's going to be greater than 20. Okay, so your test was designed for that. Okay, so you're given a significance level and you have to figure out whether you will accept or reject. So let's go out and write it down. So what is the test statistic? What is the test? Okay, so that's important, isn't it? So you can do the test. So maybe your test statistic is x bar, right? So your test is reject hit 0 if so sometimes it's easier to work with what I will call t. I'll write t as x1 plus x10 without dividing by 10. Okay, so since I'm dealing with binomial distribution, small numbers, it's better to use t instead of t by 10. It's when you go to large numbers, we'll do divided by 10, divided by n. But in this case, it's just t itself is pretty reasonable. It's good to work with t because these are all whole numbers and all that. Okay, so let's do with t. So we'll say if t is greater than c, I will reject. This is a fine enough test statistic. It's sort of related to the sample mean in some sense. Okay, so what's the distribution of t? T has a binomial 10 comma p distribution. Okay. So now C, you can see, t takes values 0, 1, 2, 3, so on, and you want to fix C only as an integer. So C is going to be either 2 or 3, or in fact, if you say greater than 2, it's 3 and above and things like that. Okay, so it's very discrete in that sense. Okay, so let's go ahead and see what the formula for alpha will work out to be. Alpha will be probability that this binomial 10 comma p is greater than c given p equals 0.2. Okay, so notice this ends up being discrete. Okay, so it's not a continuous type distribution, so you have to make a table. Okay, so how do you make a table? C and alpha, you can make a table like this. Okay, so we'll look at a few possible values for C. I mean, you're imagining P is 0.2, so C is going to be 2, 3 or something like that. So C could be 0, be always accepting it, or 1 or 2 or 3 or 4, 5. I'll stop somewhere here, some 6. Okay, so let's figure out what alpha will be. Probability that T is greater than C. It's 1 minus the binomial CDF is less than or equal to C, right? Isn't it? So it's 1 minus probability, so maybe the binomial CDF. So how do I do this? So summation k equals 0 to c of 10 choose k p to the power k 1 minus p to the power 10 minus k. So complicated little calculation. So in fact, it turns out NumPy has this has a calculation. The SciPy-Stats has a calculation for the binomial CDF, I believe. So you can check that out. It's st.binom .cdf. So we're doing 1 minus this, isn't it? 1 minus. You can check it out. I think it's 0, comma. This is always difficult to figure out where the thing will come. I think this is correct. So this is 0 and p, I think. Okay. So this should give you something reasonable. Yeah, 0.893 looks reasonable. Okay. So this is the probability that the binomial random variable takes values greater than 0, right? It's 1 minus CDF evaluated at 0. So it's greater than 0. Okay. So just to check, it's always good to check whether these things come out correctly. Let me just see 0.8 raised to the power 10. What is this guy? This guy has got to be some 0.10 something. Yeah, okay. So this is correct. So this one I can delete now. I don't need this. Okay, so this is correct. Let's 0.893. This works out to 0.893. So look at this way in which this works. So alpha comes out to be 0.893. And as I keep varying C, what am I going to get? I'm going to get different values for this value. So maybe I want to do 1. If you run this, you're going to get 0.624. Just quickly go fill this out, 0.624. And then 2. 0.322. Okay, so let's go to 3. So notice how the significance level is behaving. It's sort of 0.121. Okay, let's go to 4. 0.03. 3, 3. So suddenly it's sort of showing some reasonable behavior, and then 5, 0.0064. Okay, I'll do 6 also just for the fun of it. We'll do 6. 0.00086. Okay, so it's all very discrete. It's not like you have a continuous choice to make. And if alpha has to be 0.05, right? So here, if you fix the alpha has to be 0.05, you have to pick your C to be 4. Okay, so it implies C equals 4. Okay, so probability of T greater than C given P equals 0.2, that's what will go below 0.05. If you go to 3, you go to 0.121. Look at the jump. Okay, you can't do anything in between. I mean, you really want ideally something in between, and you don't have that room. Okay, so C is equal to 4, and you actually got C is equal to 3. Okay, so and since you got that, you're going to be accepting the null hypothesis. Okay, but really, I mean, you should feel very uncomfortable with this. This is 10 people you have sampled, only 2, and then you get all sorts of numbers, your 0.05, whatever. In fact, instead of significance level, if you go through and compute the p-value, you will get 0.121. Okay, and you seem to be okay. It's a high enough p-value. Or accepting null. We can't do anything more. Let's see. One way to view this is not to just look at the alpha and the p-value and the null hypothesis. Let's test against an alternative hypothesis to get a sense of how this is going to behave. Okay. So remember, what is type 1 error? If null is true, what's the probability of rejecting null, right? If you do thousands and thousands of these experiments with 10 samples, in only 5% of the cases, you will make this mistake of when null is true, declaring that null is not true. Right? So that's 0.05 for you. That's low enough. Okay, I fixed 0.05. Let's look at the alternative hypothesis and compute power against that. So what is power? Power, or let's look at type 2 error, right? So type 2 error, this is important. So far we never spoke about type 2 error, right? Type 2 error is where this other notion will come in. Usually we denoted beta. It's probability of accepting null given the HA is true. And what is HA? You have to provide a precise alternative. Okay. So let's say I'm saying P equals 0.3. So instead of 0.2, maybe it is 0.3. What is the probability in all these in a particular case with 10 samples when you got 3 people? What's the probability that you'll end up accepting H naught? How bad is that? Okay. So this is probability. When will you accept H naught? T is less than or equal to C given P equals 0.3. Okay. So it's the same calculation, except that it's just the CDF itself directly I need to calculate for less than or equal to 4 given P is 0.3. Okay, so let's do that. Let's do it right here. So it says T binom CDF 4, 10, 0.3. Okay, 0.85. Okay, so look at how high this value is. Okay, so your type 2 error probability is really high. When you have this just 10 people and 3 of them have told you they are vaccine hesitant, you just look at the null hypothesis, you don't worry about anything else. It seems like you have an okay test. I mean 0.05, you have gone below 0.05 in significance value, my p-value is 0.12, I'm looking all great. But test against a alternative, fix one alternative and look at your power, look at the type 2 error, look at what has happened. Probability of accepting H naught given that P equal to 0.3 is 0.85, and 85% of the time you will make this error that even though P is 0.3, you ended up accepting the null. Okay, look at how bad this situation is. And this happens because of your choice of small number of samples. You'll see the only way, because number of samples is really small, if you make alpha very low, like 0.05 and all, your beta is going to be high, okay, for reasonable alternative hypothesis. Okay, so this is something to guard against, and only way to guard against this is to increase the number of samples. Okay, so you'll see that is like a magic formula in statistics. Increase the number of samples everything goes away. Okay, so here we're going to look at the case where you have 100 people and 28 of them are vaccine hesitant, and I'm going to do the same calculation. Okay, so I'm going to look at a situation where this has happened, and let's see. I mean, it seems a little bit off. I think maybe this is okay. So let's see how this works. Let's see how the power works. Let's see how the significance level works. You'll see that it'll be dramatically better because you went from 10 to 100 samples. But it's more work for you. You have to keep calling 100 people. You may not even know 100 independent people. Think about it. It's a bit hard to do these kind of samplings. Okay, so let's quickly do it. In this case, again, the sampling and everything is the same, but for the sample, for the total, right, for T, which is actually binomial 100 comma P, okay, I'm going to make an assumption here. Okay, so I'll say it's roughly normal. Okay, you remember how the normal distribution works. N times the mean, n mu, and n times the variance, right? So 100 times P into 1 minus P. Okay, so that's the normal approximation for this total. Okay, so we'll make this approximation in our calculation. Okay, so let's go ahead and do the calculation. Alpha is probability of rejecting null, that is T is greater than C, given that P equals 0.2. Okay. So this guy is going to be 1 minus Fc of C minus 100p, which is 100p is 20, sorry, divided by 100 into 0.2 into 0.8. So that is 0.2 into 0.8 is, so I have to do a square root here. So let me just leave it like that, 100 times 0.2 times 0.8. So even here, let me just leave it as 100 times 0.2. Okay. So notice how I got it. I'm going to approximate T as normal. So T being greater than C is T minus its mean divided by its sigma being greater than C minus the mean divided by sigma, and that is 1 minus Fc. Is that okay? So this I want to be 0.05. Okay. So from here I'm going to find C. This formula by now should be really familiar to you. So from here C will be 20, which is 100 times 0.2 plus the square root of 100 times 0.2 times 0.8. 0.2 times 0.8 is 0.16. Okay. 0.16, the square root is 0.4, so it is just 4. Okay. So this whole thing, I believe, evaluates to 4, right? Square root of 16, isn't it? 20 times 0.8, yeah, that's correct. 4 times Fc inverse of 0.95, isn't it? This is the calculation. I hope I got that right. Where is our ppf? Ppf is here, times 4 plus 20. That works out to, oops, no, 0.95. I knew something was wrong there. Okay, that works out to 26.58. That's the value, 26.58. Okay, so that's our C. Now notice what has happened here in this case, since 28, T equals 28 is greater than C equals 26.58, you decide actually to the Z test at alpha equals 0.05 decides reject H0. Okay, so you're rejecting the null hypothesis, you ended up being greater. Okay, so that looks fine enough. Our alpha was low, you came to a decision, just like we did last time, we came to a decision. We didn't really not come to a decision there, but what about power? Okay, so let's see if we can calculate this power, or type 2 error. Beta is probability that T is less than or equal to C given P is 0.3. So this will work out as Fc of so 26.58 minus 100 times 0.3 by square root of 100 times 0.3 times 0.7. Okay, so this is what this will work out to. Do you see that? Okay, I hope that's okay. So it's 26.58 minus 30 divided by square root of 21. Okay, so that's the probability of type 2 error. Hopefully this is small. I've made a big case for why this should be small. If it's not small, it'll be a bit of a, oops, what did I do here? So it's ST norm CDF 26.58, actually the previous answer, minus 30 divided by square root of 21, isn't it? So you run this, you get 0.2287. So significantly lower already, right? So you're getting 0.23. Previously we had a probability of error of 85%, right? 85% of the cases you're going to make a type 2 error. Okay, in this case it's 23%. Okay, even this is not that good, isn't it? Maybe you want your beta to be even lower. Okay, so but it depends on the cases. Like 23%, maybe it's good, maybe it's bad. But I want you to compare between 10 samples and 100 samples. Look at the dramatic improvement in the power, right? In terms of type 2 error and type 1 error probability, both probabilities being low, and you can achieve it only by increasing the number of samples. Imagine if you go to 1000 samples, naturally your power will improve, your type 2 error probability will go down, type 1 error probability can also be controlled. Okay, so this notion of type 2 error probability and keeping an eye on that is very, very important. Okay, you have your null hypothesis is true, easy calculations, even with small number of samples, they seem to be driving you in one direction, you are optimizing one error, the other error can creep in. If there is an alternative nearby which is true, it can easily cause confusion for you. This is one of the central things of statistics, and you will see as you learn more and more machine learning, people will sort of cheat you with this. Okay, so they'll show you only type 1 error situations and claim that I'm doing good, I'm doing good. There will be one nearby wrong input, and then you give that, your algorithm, your test will get completely muddled. Okay, so this is a constant in statistics. You have to be very aware of this when you design any testing or any statistical procedure. Okay, so not just the alpha, not just the significance level, not just the type 1 error, type 2 error matters. And when type 2 error comes in, the whole world is out there. In this simple situation itself, you are able to see how a small type 2 error can easily make your probability calculation look bad. 0.23, even though you may say it's low, it doesn't look like 0.05, for instance, right? I would like both alpha and beta to be 0.05. For all those things, you really need good quality, high number of samples. It's very difficult to go away from those things. Okay, so it's a good lesson. So let's do one more example in this, just to drive home the point of how this helps. In fact, you can use this power calculation to find how many samples you need for guaranteeing a certain alpha and beta. Okay, so that calculation is also important. I'm going to show you one example. It will be easy enough for you to generalize from that example. Okay. So here's a situation. I've given a long drawn situation. It's a big process. Look at it. There's a company which is making resistors. It could be any other product as well. And the maximum current the resistor can carry is 3 amperes. So that's some rating that you give for your resistor. Okay. And you've tweaked something in the manufacturing process. I don't know, maybe something you changed, some input you changed, ingredient you changed. And because of that, you suspect that maybe the actual resistors that are coming out, they have a lesser current carrying capacity than 3 ampere. Okay, so you're deciding to test, and you're deciding to test with just 10 resistors. Okay, you just pick 10 resistors and you do a test, and this test, just have standard deviation. Test has a standard deviation of 0.05 ampere. Okay, so that is something you have to live with. Okay, so and your test is the following. The sample mean of the tests, if it ends up being less than 2.95, you will conclude the manufacturing process is faulty. Okay, so this is your test. You already decided what your test is. So the question asks, what is the null hypothesis? What is the alternative hypothesis? What are the samples? Okay, so the samples you can write down as x1, x2, x10. These are, what is xi? Xi is the measured current carrying capacity of ith test resistor. You pick some test resistors and you measure the capacity of that is Xi. Okay. So usually this is the test process is quite standard. So you're going to do its normal with mean mu and variance 0.05. So this is 0.05 standard deviation. So variance is 0.05 squared. Okay, watch out for the standard deviation variance confusion. Huh? This can always trip you up. Okay, that's the thing. All right. So these are the samples, and your null hypothesis is that mu equals 3. Okay, and your alternative hypothesis is mu less than 3. Okay, so that's the alternative hypothesis, samples, and what is the significance level? One can write down the significance level, and there's also a power. Okay, so you really don't want the current carrying capacity to be below 2.9. So these are some guarantees you give your customers, saying our current carrying capacity really is not less than 2.9 on average. And if various designs have been done assuming that, there's a huge safety crisis. So what happens is when something like this goes wrong, you go ahead and recall things, right? You recall, and recall has a huge cost for you. Okay, so at no point you don't want 2.9. So type 2 error against 2.9 is very, very important to you. Okay, so that's where the beta calculation comes from. So let's see how to do this alpha and beta calculation for this particular test. You've decided T10 is less than 2.9. I have some space for working here, so let's just do that. So your test is the sample mean being lesser than 2.95. So if, sorry, let me just write it carefully, reject H naught if x bar is less than 2.95. Okay, and what is the distribution of x bar? It's always important to write down normal with mean mu, and variance is going to be 0.05 squared by 10. Okay, because you are taking 10 resistors for your test. Okay, so after this, it's alpha is easy. Alpha is probability that x bar is less than 2.95 given mu equals 3, right? So this is one type of error. So this will work out as this is left sided, right? So it will work out directly as FC of 2.95 minus 3 divided by 0.05 by square root 10. Okay, this you want to keep a significant level of 0.05. So this is how. Okay, so it's not, there's no 0.05, I'm sorry. You're not designing the threshold is already decided. You've already come up with a 2.95. So this is just the alpha calculation. So let's just do this 2.95. Once again, let's go to our calculation here. It's 2.95 minus 3 divided by, okay, it's a slightly complicated, divided by 0.05 divided by the square root of 10. Okay, there you go. I think everything is right. So you got 0.0007, so 7.8 into 10 power minus 4. So that's pretty good. You've got a good process going on. 0.00, is it one more 0? Yeah, one more 0.78. Okay, good. So this alpha works out quite reasonable. Is it reasonable? I don't know. I mean, see, the resistors are made in thousands and thousands and tens of thousands. Okay, so small components, by the way. So is this good enough that you can come up with this decision with this? How do you think of this alpha as being a good enough number? Think about. So you have to think about this very carefully. So I'll come back to this a little bit later. The next problem I'll talk about how alpha could be chosen in this practical situation. Okay, so let's go to the calculation of the beta. Okay, beta asks you for type 2 error, right? So type 2 error, probability that x bar will be greater than or equal to 2.95 given mu equals 2.9. Okay, so it's this other calculation here. So this will be 1 minus FC of 2.95 minus 2.9 by 0.05 by square root 10, isn't it? It's this sort of x bar greater than, x bar is going to be normal again, and the mean is 2.9, so it's 2.95 minus 2.9 by this, so it's 1 minus that guy. So let me go to my 1 minus calculation here, 1 minus minus 2.9, so you'll get something, which is interesting. Yeah, you'll get the same thing. I could have predicted that before, right? You get 0.00078. Okay. So are these numbers good enough? Is this alpha good enough? Is this beta good enough? You have to think a little bit. Okay. So how do you decide what should be alpha, what should be beta in a real situation? Okay. Go back and think about what can happen under these two scenarios. Okay. What can happen under the scenario of a type 1 error? Okay. What is type 1 error? You have rejected null when null is true. Okay. So your manufacturing process was actually okay. It was producing good resistors. You thought it was not okay, and you went in and you want to refurbish your overall your manufacturing process. It will have a certain cost, and these costs can be high. Your manufacturing process has so many ingredients to check. It has a assembly line of people. Maybe it will cost a few tens of lakhs, and you've wasted that money. It's a cost to the company, and it has gone wrong. Okay, so 0.00078, is that good enough? Maybe it's okay. It's only 7 times in 1,000 times or 10,000 times, something like this happens. I may have made a wrong decision there. That's okay. It seems okay enough, right? So the risk is not too bad. You multiply the probability of making an error, which is 7.8 into 10 power minus 4 by 10 lakhs or so. Maybe that's your cost of overhauling the manufacturing process, and that's not too high. It's not scary high that you think you have to revisit it. The expected loss from that error is not too bad. Look at the other situation. Okay, with the power against 2.9, when the probability of a type 2 error, it's also 7.8 into 10 power minus 4. Is that low enough? You have to make your judgment here, because see, notice what happens if you make a mistake there. If by mistake you accept null when the alternative is true for 2.9, it's a safety issue. You're going to do recall. You're going to go and compensate customers. So somebody's component would have blown up already, and you have to pay insurance, this, that. Your cost is going to go to crores, maybe even lawsuits, right? You have to go fight against this guy and that guy. Your cost is going to go to the crores. So a type 2 error here, particularly with a safety concern like this, is way more critical. And 10 power minus 4 is simply not going to cut it, because your cost is going to go into crores if you make an error here. You better be absolutely sure you're not making error with beta. So the type 2 error. Okay. So notice how in the actual situation, depending on the application, you have to have a judgment of how much of type 1 error I can tolerate, how much of type 2 error you can tolerate. If you ask some other types of socially relevant questions, different types of questions, this kind of trade-off you may not be able to set in. But for industrial processes like this, when the safety concern, when the cost of making a type 1 error is sort of clear to you, you have to bring that in and sort of multiply it, decide the error based on that cost. If the cost is going to be crores, your probability of error better be 10 power minus 10 or something lower. Okay. So while these alpha beta look low, they may not be low enough in some applications, particularly in this application. When the risk is so high, it may not be low enough. Okay. How do you get alpha and beta to be lower? How do you control them even further? You can do that using the number of samples. Okay, remember, the number of samples also has a cost for you. Okay, if you test 10 samples, every test will, it will cost you some money. Okay, so you have to account for that also. You want to minimize n. You want to keep as low an n as possible. Okay, but more critical are the type 1 error probability, type 2 error probability. So here is the same problem. I'm saying you have to decide how many resistors you have to test, and generalize the test. Don't say Tn is less than 2.95. Maybe it's good enough, but let's say less than C, some C. I'm willing to play with that C. Okay. Can you determine suitable values? I mean, you want to keep n as small as possible, okay, so that you can be reasonably sure, but I want the significance level, the probability of type 1 error, to be less than or equal to 10 power minus 6. Okay, maybe my cost for overhauling the manufacturing process is very high, and there's also a value cost. When you overhaul a process, you're stopping it, right? When you stop a process, that costs a lot of money for the company, right? You're not producing money, wasting money, so that wasting time, and so that's also something to worry about. So 10 power minus 6, maybe I'm comfortable. But probability of type 2 error, this safety issue, I want to keep at 10 power minus 12. I want to keep really, really, really low. I don't want to play with that. So in these kind of scenarios, how will you decide number of samples? You'll see number of samples will come out to be a very nice sort of way in which you can determine it. Okay? So I want to work this out a little bit and show you how this would possibly work. Okay? So everything else remains very similar, except that your x bar is going to be normal, mean, mu, and your test process is 0.05 by, in this case it's square root n, no, 0.05 n squared by n. Okay, n is the number of samples that you got. Notice this 0.05, right? If you had a testing process which was more predictable, its standard deviation was lesser, you should invest in that too, because that can also reduce your variance, and this variance is what is causing a lot of problems for you, right? So keep that in mind. I mean, you should sort of identify what is causing problems. Okay, so this is x bar, and then your test is always it's less than c. So alpha is probability that x bar goes less than c given mu equals 3. Okay, so this would work out as fc of c minus 3 by 0.05 by square root n. Okay, so whatever n is, you will get this. So supposing I want this to be equal to 10 power minus 6, let's say, or maybe less than or equal to. Let's put less than or equal to. Okay, so in this case, what should happen here? You can invert. Fc is monotonic, so this will be c minus 3 by 0.05 by root n is less than or equal to Fc inverse of 10 power minus 6. So from here you will get c is less than or equal to 3 plus 0.05 by root n. Fc inverse of 10 power minus 6, let's just do that, instead of just carrying on with that. 10 power minus 6, let's do that. That will work out to some minus 4.753 times minus 4.753. Okay, so that's one equation that you got. Okay, so let's number this equation. 1. It's nice to number these things. So I want c to be less than or equal to this, and n, the calculation for n will work out whatever n you plug in here, you should get. So you can do this multiplication and figure out for different n you will get different c. Okay, so it's easy enough to see this. What about beta? Beta is probability that x bar is greater than, maybe this one was less than or equal to c. No, greater than. That's okay. So greater than or equal to c given mu equals 2.9, and that will work out as 1 minus fc of c minus 2.9 by 0.05 by root n. Okay, thus that will have to go less than or equal to 10 power minus 12. You can sort of do this in multiple ways. So one way to do it is to write this guy. So this is 1 minus 10 power minus 12 and fc inverse and all is a bit tricky. So what works better? Maybe it would work. I don't know if numerically if that works. So sometimes fc inverse of 1e minus 12 is better than fc inverse of 1 minus 1e minus 12. Let me see. 12 is not too high. Let's see if this works or if this gives me a nonsensical answer. No, it works. It's okay. 7.034. Okay. All right. So then now this will give me fc. So this implies fc of c minus 2.9 by 0.05 by root n is greater than or equal to 1 minus 10 power minus 12. Again, you can do a fc inverse, but fc is a monotonic function. So c you will get is c minus 2.9 by 0.05 by root n. I just did the calculation for you, is greater than or equal to, what was that, 7.034. 7.034, right? 7.034 odd, okay? So this implies what? This is my second equation. C is greater than or equal to 2.9 plus 0.05 by root 10 times 7.034. So notice how neatly these two equations come about. So this is what you have to do. You keep picking your n such that, okay, I want C greater than or equal to this, I want C less than or equal to this, and as I keep increasing n, supposing if I make n to be like a very, very large number, any value between 2.9 and 3 will work, right? Because see the 0.05 by root n minus 4.77.3, if n is like 1 million, then that additional thing is going to become so small that I can pick any value between 2.9 and 3. I could pick 2.95, it will comfortably work. But that's not the point. What am I trying to say? I am trying to minimize n, right? I should be finding the least n that will give you this. So how do you make this work? C is less than or equal to something, C is greater than or equal to something, right? How do I minimize n? You can equate these two things, okay? So C needs to be greater than or equal to this 2.9 plus this. C has to be less than or equal to 3 point something. How do you find the optimal value for n? You just make sure that this 3 plus 0.05 by root n minus 4.7, this thing on the right hand side is equal to this right hand side here. So then that gives you the optimal choice of n, okay, best choice of n. So think about that, why that is true a little bit, right? So as you keep increasing n, like I said, the upper bound will go towards 3. So maybe I should draw this picture for you. So you have 2 here, you have 3 here. So this one I will call it C upper bound. This one I will call C lower bound, okay? So as n increases, so you may have, you may have C upper bound here, you may have C lower bound here, okay? So this is not very optimal, right? So for some particular value of n, you may get this. So there is a gap here, okay? So if n is large, this is what you will get, larger than necessary, okay? At the optimal value, both of these will be the same, CLB equal to CUB at best n, okay? So this is what will happen, right? Because this is 3 minus something, this is 2.9 plus something. As you increase n, both of these are going away from each other. At some point, they would be the same. If they cross over, then there is no test that will achieve this, okay? It may happen that CLB goes to the right of CUB. Then you have no test. At those n's, you will not have a test. So values of n below this best n that I find, there will be no test that will give you 10 power minus 6 and 10 power minus 12 for the type 1 and type 2 errors, okay? So let's go ahead and do this. If you can equate this, if you equate this and sort of simplify, you will get one final very nice answer. So let's just write that down. So I'm going to equate this in my head and do one simplification. Anytime I do this, people complain about how I'm doing some, seem to be doing some magic. There's no magic here. So I'm going to equate these two guys, lower bound and upper bound, and take 2.9 to this side. I will get 0.1, right? 2.9 to that side, 3 minus 2.9 is 0.1, and that is 0.05 by root n times the sum of these two things, right? Because this came to this side, so it got added up. So 4.753 plus 7.034. So you will see something like this as a formula stated in many stats textbooks. They will state this as a formula for finding what n is, okay? So it's, in general, it's very easy to derive, and this is how it works, okay? From here you can figure out what n is. I think n will come out to be roughly about 36 or so. You can check this, okay? Check, okay? And maybe I should just do this, okay? So I'm being lazy here. So it's 0.5 times 4.753 plus 7.034, I think squared, right? 34.73. Okay, so it's not 36. Okay, so you need to test 35 resistors, and 35 is sort of the optimal value. What do I mean by optimal value? If you do less than 35, you cannot achieve both alpha and beta being the range that you want, alpha being less than or equal to 10 power minus 6, beta being less than or equal to 10 power minus 12. If n is above 35, you will have a bigger gap. You will have a range of values at which you can achieve this, and if n is equal to 35, it's sort of optimal. These two are roughly the same. So for 35, you can go ahead and compute the values of C. You will get something around 2.95. I'll leave that as an exercise. You find the C corresponding to this 35, which gives you both of these values. Okay, so hopefully this problem sort of was illustrative. These kind of calculations are very standard in some sense. If you know the type 1 error, type 2 error that you want, how do you find n and C? But more than that, I want to emphasize this type 2 error a lot. Don't forget the type 2 error as you keep designing your methods, because they can really come and cause so much confusion in any very nice procedure that you have. Okay. Okay, so the last problem that I wanted to tackle here is again a sample size problem, very similar to the previous one. I'm just making it in a college context just to make it interesting. Okay, so the average CGPA of students in a college, maybe somebody is reporting it as 8 with a standard deviation of 1. Okay, you have a suspicion that it might be lower, maybe 7.5. You think 7.5 is could be one possibility. And you want to sample students to find their CGPA. Okay, you want to sample the students, find it and see if this 8 is really true. Okay, how many sample size, what sample size will you pick for a significance level 0.05 and power of 0.95? And supposing if you want to have the alternative be as low as 7, will the sample size change, and how does it change? Okay, so sort of simple calculation similar to before. Let's see if we can do it a bit faster. Okay. So the samples are x1, xn, you don't know n, and you want to say it's normal mu and variance is 1, right? So x bar is going to be normal with mean mu and variance 1 by n. This is your x bar, and your null hypothesis is always mu equals 8. The first alternative we are looking at is mu is less than 8. Okay, so alternative is always mu less than 8. Okay, so that's also true. And your test is going to be reject h naught if x bar is lesser than c. Okay, so your alpha you want it to be 0.05. So let's figure out how c will be determined. C is going to be determined just by alpha in this case, right? Once you fix a significance level, okay, n is also involved. Both alpha and n will play a role. So C and n, there will be a relationship because I want significance level 0.05. So it's probability that x bar is less than C given mu equals 8. Okay, so this one is FC of C minus 8 divided by 1 by root n. Okay. So this implies, so significance level, remember it's always good to write this as, okay, let me just write it differently, like exactly like before. I want it to be say less than or equal to 0.05. So this gives you some sort of an inequality, right? So, or maybe we'll say equal to, doesn't matter. So you do FC inverse of 0.05, we've seen that before. So C equals 8 plus, what is FC inverse of 0.05? We have seen this, we have not seen this. Okay, we've seen this 0.05, it will come out as negative. I pressed the enter there, so let's do this. Minus 1.645. Actually didn't know this, but anyway. So you're going to get minus 1.645 by root n. So this is your formula for C. Okay, so this is something to keep in mind. You can hold this as 1. This came from alpha. Okay, I want a power of 0.95, which means beta also has to be 95. So in the first case, beta is probability that x bar is going to be greater than or equal to c given mu equals 7.5, okay, and that guy is 1 minus fc of the c minus 7.5 by 1 by root 10. Okay, we will assume your standard deviation is also 1, okay, 1 by root 10 whenever you do this measurements. So 1 by root 10, and this you want to be also 0.05, isn't it? So this is the same thing that we expect here. Okay, so you see this gives you two equations, two variables. C would be a constant, you just equate, you're going to get n. Okay, so same as before, and you'll see the similar sort of formula will work out. Okay, so you do this, you're going to get fc of c minus is 0.95. So you're going to get c to be equal to 7.5 plus 1 by root 10 times fc inverse of 0.95, and that fc inverse of 0.95 is, we know this, I think it's 1.97. No, 1.645, 0.975 is that, okay, 1.645. So you see that, 1.645 by that. Okay, so because of 0.05, you will get the same answer here. You can see why this has to work out like that. Okay, so this is 2. So 1 and 2 will give you, you equate these two again. When you equate this, I'll subtract this, bring it to this side, you do that calculation. So you see 0.5 equals, okay, the sum of these two. So it's like 2 times 1.645 by root 10. So this is a standard formula. So you get n to be, okay, so let's just write this down. I did one squaring here, right? What is the formula here? 2 by 0.5 is 4. 4 times 1.645 squared, right? 4 times. So it's not too bad. You're getting some answer here. So it says 43.29. So 44 roughly, and is 44. So you need 44 students, and then you can assure yourself of a type 1 error which is 0.05, type 2 error which is 0.05 again. Okay. Now supposing your alternative hypothesis is 7, you want power against an alternative hypothesis of 7 and now 7.5. What do you think will happen? Intuitively, what will happen? Think about this intuition. This is very, very important. Okay. So this intuition about distributions and how it works is, I think, more important than even the calculation. Okay. What is this intuition? I'm suspecting the null to be 8. My alternative is 7.5. It's close to me. I needed 44 samples to make sure I can distinguish between these two, both in type 1 error and type 2 error. Okay. I need 44. Okay, because it's 7.5 is close. My alternative is going away. I want power only against an alternative which is farther away. 7, okay, 8 and 7. Will I need fewer samples or will I need more samples? Right? Type 1 error sort of is the same because I'm around 8. Type 2 error will become better off just because my alternative went far away, right? So intuitively it appears that you should need lesser samples. Will the calculation bear out? Let's check it out. Okay. Case 2, beta became 1 minus fc of c minus 7 by 1 by root 10. That needs to be equal to 0.05, which implies I could have written this directly. C equals 7 plus 1.645 by root 10. It will, no, I mean, you can see why it has to. So 1 and 3 together will imply 1 equals 2.2 times 1.645 by root 10. So this implies n will be roughly. So instead of 0.5, I made it 1. It will be, previously we had 4 times 1.645 squared. Now we'll just have 2 times 1.645 squared. So it will go down to 11, I think. Isn't it 11? I think so. So n will be roughly 11. Okay. So if you want power only against a hypothesis, the alternative which is farther away, then with fewer number of samples, you'll have more power. Okay, that intuition is very, very, very important, and it's very simple also, right? See, as supposing 7.5 became closer, if you really need power to distinguish between 8 and 7.8, no, it's, why would you want to do in CG? It doesn't matter, but in real life applications you may want it, right? This could be a medical treatment, and this could be some very critical parameter in a medical treatment. Then maybe you want to bring your alternative close when you want to measure your power. Okay. So these kind of things will show up in machine learning also. So there are these ideas called adversarial learnings, etc. So type 2 error is very important to control, and the number of samples you need is controlled usually by this trade-off you have between type 1 error and type 2 error. Okay. So hopefully this gave you some interesting things to think about when you design a hypothesis test, the two types of error, the trade-off between them, the centrality of the number of samples, and the importance of understanding how to set these things is also very, very important. Of course, you may have other type of data in a social context where all these type of things may not be very easy to do and all that, but this is important, and your intuition for how good a test is should always come based on this. How good is my type 1 error? Am I doing well on my type 1 error? Maybe p-value sort of measures that. What about type 2? What if there's an alternative which is close by, which also explains this data in a very reasonable way, and my type 2 error is very high? Then also it's bad, right? It's a very, very risky thing to do. Quite often in studies, people ignore this type 2 error. Just look at type 1 error and make conclusions from that. It's really, really, really risky. Okay, so let's conclude this lecture with that thought, and thank you very much.